Hello, it's Pat's Paper Guy here. I'm going to be solving this Electronics GCSE paper. It's an E2 paper from 2017 by WJEC. Question 1. The diagram shows a capacitor-resistor network, so it can be used to produce a time delay. Which one of the following would increase this time delay? Well, if you increase the values of R and C, the time delay is governed by R and C. So if you increase R and C, then you would increase the time delay. So if you double the value of R and keep C unchanged, that would increase it. Double the value of R, half the value of C, they cancel each other out. Same there. That would just make it smaller, and that would make it smaller. So it's that one there. Why is this NOT gate included in the circuit? It reduces the time delay. No, that depends on R and C. It increases the current taken from the capacitor. No, it decreases the current taken from the capacitor there. It keeps the time delay unchanged when current flows from the output. That's true. It produces a low voltage at the output when the switch is pressed. Nothing to do with that. So it's that one there. If you don't draw any current off here, you don't change the voltage across this capacitor here. Question 2. Here are 4 signals produced by an A-step. We'll just check the scales, because sometimes they mess around with the scales. This time they've got the exact same scales. Which has the longest time period? So we're looking for the widest pulse, which is this one, isn't it? B. Which one has a period of 1 second? The one with a period of 1 second is this one here. So that's C. Which one has an amplitude of 6 volts? Well, the amplitude of a pulse like this is from the middle to the top there. Even though it's the pulse height, we call that the amplitude, even though technically it's not, it's the pulse height. Part B, which are the following 555 for a monostable, so you just need to know these off by heart. It looks like this one. It's got 1 resistor, 1 capacitor. That's an A-stable. These two are some sort of latches or something that doesn't even work. I don't know. So it's this one here. Question 3. 7-segment display here. Got 2 things we need to do. So display 7-segment displays light when they receive logical 1 by adding 1s or 0s, complete for getting an F. So we need that, and that. So we got A and G, F and E, and all the rest are zeros. And we want the number 3, so that would be A, B, C, D, and G. So A, B, C, D, and G will give us the number 3. That's that. Question 4. We've got a block diagram here. Why is it best to use a BCD binary coded decimal counter rather than a binary counter? So it's got nothing to do with the speed. It's because it only counts up to from 0 to 9, so it's binary coded decimal. So it resets automatically on the 10th pulse, that's true. It outputs letters and numbers, no, it doesn't do that. It's easier for humans to understand, well, decimal's easier for humans to understand, not binary. So it's that one there. This is a decade counter now. Here's the pin out for it. Why is this type of counter unsuitable for the single-digit decimal counting system? Well, the problem with this is that only ever one of these outputs is high at once. So it's not that it counts up in tens and not units. It cannot be reset. It can be reset automatically. Each output of the counter goes high in turn. It's that one there. Every 10th count, it outputs a pulse from its clock pin. No, it doesn't. So it's that one there. Here we have a D-type. Complete the following statements about the action of the rising edge D-type flip-flop by inserting either a 1 or a 0 in the boxes. The Q output of the D-type is initially at logical 0. The data is set to logical 1. When the clock input changes from a 0 to a 1, the output Q bar, so the Q bar is at a 1 to start with, will change from a 1 and it will go to a 0. That will become a 1, so that will become a 0. A rising edge triggered D-type flip-flop is set up as a latch. It receives a clock signal shown in the top graph here. Use the axes provided to show the corresponding Q and Q bar output. So we need to wait till we get a rising edge on the clock, which is there. And that's when Q will go high. Try to make this so it's easier to read. And Q bar starts high and will go low. There. This one goes along there, along there. If you draw your rising edges in first, it makes it a lot easier. Question 6. D-type can be set up as a divide by 2 subsystem. Which of the following shows the connections needed to do this? So we need Q bar back to D. So Q bar back to D is that one. Complete the graph of the divide by 2. Okay, so this is once again going to change on rising edges, like so. So it's going to go up there, that's odd. That says 1 there, but they've only got it going to 2/3 of the way up. Never mind. So every time we have a rising edge here, is when the output changes. Like so. At an airport, an electric buggy is used to transport people and their luggage. It has a warning buzzer which sounds when it reverses. Buzzer. The flowchart that controls the reversing is shown below. Reverse is selected for 3 seconds only. Describe what happens over the 5 seconds after reverse is selected. So what's going to happen then? It's going to come down here. Is reverse selected? Yes, it is. It's going to reverse the thing, make it buzz, do that for 1 second, turn the buzzer off, do that for 1 second, then it's going to go back here. Now that's 2 seconds will have passed when it does that. So now it's going to come into here. The reverse thing's still on, so it's going to keep the reverse motor on, beep the buzzer for 1 second, turn the buzzer off for 1 second. So now 4 seconds will have passed, and it's still reversing. So even though you've only selected reverse for 3 seconds, it actually is going to be reversing for 4. Then it's going to come back here. Now the reverse signal is no longer selected, so it's going to come into here. It's going to turn off the reverse motor, and that's going to stay like that for the remaining second. So describe what happens over the first. So it goes into reverse. The buzzer is on for 1 second, off for 1 second, on for 1 second, and off for 1 second, and then that's after 4 seconds have passed now. So then after 4 seconds have passed, the reverse motor stops. So that's not a very good design, is it? So maybe a better way of answering that would have been to draw a little table. Oops. So we could have had 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, And we could have reverse, that's on, and off, and buzzer is on first, then off, then on, then off, then off. Maybe that would have summarised it a little bit better. Part B. So we've got a new flowchart now. So we enter here, we set this count to 0 as variable here. We ask if it is reversing. If it isn't, we'll just go around here. If it is, then it comes down to here. Now it hasn't set the reverse motor on yet. So it's not reversing yet. And it's going to go, is the count less than 5? Well, it's going to be 4. Sorry, it's going to be 1, so we set 0 there and we added 1 to it here. So it's going to be 1 at the moment. So we'll go here, we'll buzz for a second, off for a second. Is it still in reverse? Yes. The count will now be 2. So it will buzz again. Then the count will go up to 3, 4. And then once it hits 5, it will go, is the count less than 5? And the answer will be no. So it will actually turn the reverse on and the buzzer will be on permanently as it goes around here until you unselect reverse, when it will turn the reverse off and reset the counter to 0. What it doesn't do is turn the buzzer off, so the buzzer will never ever turn itself off. So that's a flaw. Okay, the reverse gear is selected. How many times does the buzzer pulse before the buggy moves? So it adds 1 here, so it's going to pulse once. Then it adds 1 again, so it's going to pulse twice. Then it adds 1, so it's going to pulse 3 times. Then it adds 1, so it's going to pulse 4 times. Then it adds 1, and when it does that, it goes down there, so it's going to pulse 4 times. During testing, while the buggy is moving backwards, the gear lever is moved out of reverse. The buggy stops moving. 2 other things happen. State 1 which is necessary and 1 which is a problem. So we already said that the problem is that the buzzer stays on. Right, so 2 things happen. The buggy stops moving, the counter's changed back to 0, so it's going to beep again once it... So I think that's what it's after there. The count is reset to 0. Okay, so nothing turns the buzzer off, but it does come here, and then the counter is reset to 0 there. Okay, that's significantly harder than the 2016 paper. Question 8, public address system contains all of this. This is the standard block diagram you need to know off by heart. So we just need to know this. In a system, the electrical signals converted into sound by loudspeakers. The one that combines them is the mixer, and the one that boosts voltage signals is the preamplifier. The one that boosts current is the power amplifier. Circle the correct answer. The range of frequencies that an amplifier can amplify over is known as the bandwidth. And a public address system uses a voltage amplifier to boost from 20 millivolts to 240 millivolts. What's the voltage gain? So it is gain is equal to V out over V in, which is equal to 240 divided by 20 millivolts in each case. So that cancels with that 12 times, so it's 12 is the gain. The gain has no units, it's just times 12. Question 9, we've got a non-inverting amplifier. Which one is the non-inverting amplifier? So for a non-inverting amplifier, because it's an amplifier, we need negative feedback. So it can be either that one, but not that one. That's got positive feedback. And it's non-inverting, so the input has to connect to the non-inverting terminal, which is that one, not that one, not that one. So it's this one here. What's the voltage gain of the non-inverting amplifier? Well, the gain is equal to 1 plus RF over R2. So that's equal to 1 plus 100 over 10,000 in each case. That's 11. The graph shows the input and output voltages for a different amplifier. So this is a non-inverting one as well. What's the voltage gain of this amplifier? So we just need to find the peak there, which is at 2 volts, and the peak there, which is at 12 volts. So it's 12 divided by 2 is equal to 6. Oops, there's no unit. It's going to write volts then. There's no unit, it's just 6. Okay, question 10. This is a little bit off spec because it's about memory, but a warning sign is made up of a number of sections used to display letters such as stop. Each section has 7 rows, each containing 5 LEDs. So that means there are 35 LEDs on each segment here. The LEDs are controlled individually using a memory IC that stores all 26 letters of the English alphabet. The one below is lighting the LEDs needed to show the letter O. How many address locations are needed to store the alphabet? Well, there are 26 letters, so we need 26 locations. How many data bits must each location have in order to control the LEDs? Well, there are 35 LEDs, and they all have to be either on or off, so each location must have 35 bits. Question 11. The circuit diagram shows part of a sequence generator. The purpose of the table is to summarize the behavior of the system. So complete the C, B, and A columns with this. So we need to just count up in binary, so it's going to go like that. So it's resetting on 1, 1, 0, and that's going to 0, 0, 0. Okay, that might be useful. Complete X and Y columns with either a 0 or a 1. So X is not C. So it's the opposite of this one. So it's 1, 1, 1, 1, 0, 0. And Y is the NAND of A and B. I always just do this in the margin, just so I don't make any mistakes. So A and B, so it's those two. So whenever they're both 1s, the output is 0. In all other cases, the output will be 1. For how many seconds after the counter is reset does C remain at logical 1? Oh, sorry, logical 0. So it's reset here, 1, 2, 3. It's a 3 hertz. So it's reset, and then 1 second later it moves to here, 1 second later it moves to here, 1 second later it moves to here, 1 second later it moves to there. So it's 4 seconds in total because it's a 1 hertz thing there. The system resets on pulse 6. What type of logic gate is needed in box Z? So we've got B and C here. So B and C both, it's the first time they're both high, so we want an AND gate there. So there's the AND gate. Right. When connected to a 5-volt power supply, the output of a Schmitt inverter. So changes from a logical 1 to a logical 0 when a rising input voltage reaches 3 volts. So let's mark that on the diagram straight away, shall we? So that's there. So that's going to happen there. Changes from a 0 to a 1, so that's going to change from a 1 to a 0. Getting ahead of myself here. And it changes from a 0 to a 1 when the falling input reaches 1 volt. So there's 1 volt there. So that is the point at which it changes back again. Like so. Now it goes to 5 volts because it's set up here, the 5-volt power supply there. So when it goes above 3 volts, that's when it first changes, and when it goes below 1 volt, that's when it changes the second time. It's an inverter, which means that when you are in this region here, when this is low, you've got a high output. When this is big, you've got a low output, and when this is low again, you go to a high output because it's an inverter. Question 13. An astable circuit has the following RC network. Okay, convert 10 kiloohms to ohms, that's easy, 10,000. Convert 100 microfarads into farads. So this is quite straightforward, but if you don't know how to do this easily, you can do it like this. So you put in 100 times 10, micro is minus 6, and you press equals, and then you can press the ENG button, and if you press the shift ENG button, it goes back until it's times 10 to the naught, so it's 1, 2, 3 noughts. So it's this one there. Okay, another way of thinking about that is that you have 0.0000001 is 1 microfarad, so 100 microfarads is that. Okay, so that's 1 microfarad, so 100 micro whatever is that. Right, so we just need to use this equation in the next one. So let's do that. So we're going to have F is equal to 1.4 over, so R1 is 10,000 plus 2R2, so that's 30,000 times by C, which is 100 times 10 to the minus 6. So 1.4 divided by 30,000 times by 100 times 10 to the minus 6 gives us 4.666. So that's 47 hertz to SF. Sorry, 0.4666. So that rounds up. Next, a 2-bit counting system uses this astable circuit, or an astable circuit. The counter is initially reset and a falling edge triggered. There you can see it's falling edge triggered. Output A is the least significant bit. The upper graph shows the pulses arriving at the counter. Draw the outputs A and B. Okay, so once again we need to mark on the falling edges here, like so. I'm going to use pencil this time. And then we just trace these down like so. Right, it says initially it is reset, so both of these start at 0. Then the least significant bit will count 1. And then this will stay still. So if you think about the counting, we're going 0, 0, 0, 1, 1, 0, 1, 1, like so. So that's 0, 0, this is 0, 1. Now we're gonna, this one is gonna fall like that. That falling edge triggers that to rise there. This falling edge makes that one rise there. That one changes there. So now we have 1, 0 there, 1, 1 there, and back to 0, 0 there. So that's counting properly. Right, we have the graph drawing question here. We've got an inverting amplifier, voltage gain of -5. So this is the input signal here. The axis below draw a wave to the corresponding output signal. So we've got a peak there, an amplitude of 0.1. So we times that by -5. So we're going to go to minus 0.5 and plus 0.5. And it's going to go down first because it's going to be there. So we don't need to worry about the times because it's told us what the times are. So we're going to go through that point and that point, and when this is at plus 0.1, this should be minus 0.5, Then here we need plus 0.5, 0, minus 0.5 there, 0, plus 0.5 there, 0, minus 0.5 there, plus 0.5 there. The easiest way to do this is to turn your paper around so that you can move your wrist. Like so. Right, now we need to create the amplifier with a gain of minus 0.5. So the gain equation is equal to minus the feedback resistor over the input resistor. So if we have minus 5 would equal minus 100 over 20. So we need to put the 100 in here, 20 in here, and here we can just connect this to ground. The plus has to be connected to ground. That means that the negative feedback will make that 0 volts there, so the op amp will do its job. Okay, a transistor switch turns on a fan automatically when it gets too hot. So let's do a quick sketch of the thermistor's response. So that's hot, cold, and that's its resistance there. Part of the circuit is shown below. So when it is hot, we want this voltage here to be big. I really ought to read the rest of the question. Part of the circuit is shown below. Complete it by drawing suitable components. The system must switch on when the temperature gets too hot and allow the user to adjust the switch on temperature. So to adjust it, we're going to need to use this one here, and we're going to use the thermistor. So it's just a matter of figuring out which way round we want them to be. Now, if we want it to turn on when it's hot, then the resistance here will be small. When it's hot here, the resistance of this will be small, so we want that up here to make that value closer to that value. So we want the thermistor in the top, and we want the variable at the bottom, like that. A different transistor switch is used to interface with a logical system and a lamp unit. Assume that the transistor is just saturated. So just saturated means that the transistor voltage is 0 volts. So that means that that voltage there is 12 volts, all of it. When the logic system outputs a logical 1, Vin is 10.7 volts. Okay, this produces a base current of 2 milliamps. What's the voltage across resistor R? We've got to remember when this is on, there's a voltage drop across here of 0.7 volts. So it's 10.7 here, take away the 0.7 on that side, equals 10 volts. So that's going to be 10. What's the resistance of the base resistance? R is equal to V over I, which is equal to 10 divided by 2 times 10 to the minus 3, is equal to 5,000. So it wants it in kilo ohms, so that's 5. The transistor has a current gain of 50. Calculate the collector current when the base current is, so this is easy, IC is equal to HFE times by IB. That's equal to 50 times by 2 milliamps equals 100 milliamps. So 100 goes there. And that is the end of the paper. Well, thank you very much for watching. If you found this useful, then please do like it and subscribe and tell your friends about it who are also studying electronics. I also do physics videos as well. So if you have any questions, then post them in the comments section. Good luck in your exams.